Okay, so let's get started. So last time we were looking at the Schwarzschild metric, okay, and the argument that I gave you but I did not prove is that there is a theorem that guarantees that this is the unique solution to Einstein's equations, which has spherical symmetry. Okay, and how do we define spherical symmetry in a way that is independent of coordinates? Well, the way you define it in a way that is independent of coordinates is that you say that there are three Killing vectors, Rx, Ry, Rz. Okay, these are global Killing vectors, and these Killing vectors have the property that they satisfy some Lie bracket, okay, which was something like this with cyclic permutations. So if you say that your manifold has these Killing vectors, okay, and these Killing vectors satisfy this SO2 algebra, then you say that your manifold has spherical symmetry. Okay, this is a coordinate independent way of saying that you have spherical symmetry. And the Schwarzschild solution is the unique solution, okay, that that describes such a situation which solves Einstein's equations in vacuum. Okay, this is the important point. Okay, it satisfies Einstein's equation. So there are other solutions that you can get that don't satisfy Einstein's equations. We're interested in the ones that solve Einstein's equations. And we're also interested in where we're solving in vacuum. That is, there are no sources present. Which means you can keep going inward in radius till you encounter, let's say, some matter or energy, right, which is distorting your space-time. Outside of that, as long as you have spherical symmetry, this solution should work. Okay, and this is a family of solutions where M parameterizes, okay, a particular solution. Okay, but they all vary based on just the choice of this constant M. Okay, so today what we're going to do is we're going to look at the geodesic equations for this metric. Okay, so we said already that this metric seems to break down at R is equal to 2gm. So the coordinate path seems to be valid only above R is 2gm. Okay, so for the moment we'll study geodesics outside of this region. Okay, we'll see what happens for R greater than 2gm. Okay, so now we'll work in the affine parameterization where our geodesic equation is something like this, where and then you can work it out in coordinates. Okay, in some coordinate system, if I have a tangent vector which I denote as x mu, okay, your geodesic equation looks like this. Dx nu d lambda dx rho d lambda is 0, where lambda is some affine parameter. Okay, and so x0 is t. Okay, in our coordinates, x0 is t, x1 is r, x2 is theta, x3 is phi. Okay. So you have these four coordinates. So you have some geodesic equation. I've written down the first one. Okay, what you have to do to work out the geodesic equation is, of course, you have to work out these Christoffel symbols. Okay, and there's a sum over nu and rho, which means that in principle, for each of these you can have contributions from things like dr lambda, dt lambda, d phi lambda, d theta lambda. Okay, those could show up over here because the index nu and rho are summed over. So you have to work out the equations. You have to first work out the Christoffel symbols that's given to you as homework assignment, and then work out the geodesic equations. Okay, the result is a very ugly mess, but okay, it's some set of equations which are, I mean, at least the procedure to do it is straightforward. Okay, so you have these equations. And in principle now, if you want to find the trajectories of a particle that are in free fall, that is inertial particles, you just have to solve these geodesic equations to find the trajectories of particles. Okay, so in principle, you just have to solve these equations given some initial conditions, and you will obtain t as a function of lambda, r as a function of lambda, theta as a function of lambda, and phi as a function of lambda. This is a parametric description of the trajectory. Okay, normally we think of a trajectory as tell me x, y, z as a function of t. Okay, now what we're saying is tell me r theta phi and t, but instead of telling me r theta phi as a function of t, tell me all of these parametrically in terms of some parameter lambda. Okay, that's all we're doing. And if you want the trajectory as a function of t, you eliminate lambda. Okay, but that's it, right? In principle, you just have to solve these equations. Okay, but that seems like it's a straightforward thing to do, but the equations are horribly messy. Okay. I mean, there are a couple of differential equations, right? Because this involves d square t d lambda square, and it has a dr d lambda and a dt d lambda. Okay, so these are, and even the coefficients depend on R. Okay, because all the derivatives of the metric will be R dependent. Well, also theta dependent, because your metric also has theta dependence. Okay, this d omega square is d theta square plus sine square theta d phi square. So your metric depends on both theta and R. Okay, so in general these Christoffel symbols will depend on R and theta as well. Okay, so it is quite messy to solve these. Okay, these are coupled differential equations with R and theta. Okay, but so in practice this is rather difficult to do. Okay, if you want to solve this. But what you can do is whenever you have a situation with symmetry, right, the entire point is not just to solve equations, because for example, if you solve in Cartesian coordinates something with spherical symmetry, it looks horribly complicated. But if you use the symmetry to simplify the problem, okay, then you can solve these equations. So that's what we're going to do. Okay, we're going to use the isometries. Okay, isometries are the symmetries of the metric. So if you recall our equation for the killing vectors, it was del u kv k nu, del nu k mu is 0. Okay, and now what you can do is, so k mu is a killing vector. Okay, and what are the killing vectors? Well, we said there is rx, ry, rz. These are 3 killing vectors. Okay, each one has an index mu. But in addition to this, we said that Birkhoff's theorem guarantees that there's a 4th killing vector, which is a time-like killing vector. Okay, which is partial t. So you have 4 killing vectors. Okay, so now what you can do is, supposing now I take the tangent along the trajectory. Okay, so the trajectory has some tangent. This tangent vector is a 4 vector. Okay, it is in coordinates. It's this. Okay, it has components dx mu, d lambda, partial x mu. Okay, this is the tangent vector to the trajectory. So this is a trajectory. Okay, and what we can do now is take those tangent vectors, and you can think of this as a 0, 2 dual vector. Okay, which I now dot with, or I now act this on 2 vectors. I act it on t and I act it on t. Okay, where t is the tangent vector to the trajectory. Okay, so you can always do this, right? Because this dual vector takes in 2 vectors as input and returns a complex, a real number on the manifold. Okay, so in components, what we're doing is we're taking t nu, del u k nu plus del nu k mu is 0. Okay, that's what we're doing. Now, one thing that we know is for this affine connection, right? If I have x mu del mu, okay, then this is just del x. Okay, that's the property of the affine connection. So this is derivative with respect to t, okay, of k nu with the t outside. But then I can pull this other t inside, okay, and write it as t mu k mu. Why can I do that? Because I know that for the tangent vectors, del t is 0. Okay, for an affinely parameterized trajectory. This is the definition of the geodesic equation. Okay, so I can pull the t inside. So instead of having t something which is schematically like this, I can pull this t inside, and this t is dotted with this k. So I get del t k. Okay, and that's it. What we have at the end is that along the trajectory, if you take the derivative, t dot k, okay, where t is a tangent vector, k is a killing vector, t dot k, okay, this dot product of the 4 vectors t and k, that does not change. Okay, that's a constant along the trajectory. Okay, del t of that is 0. So where t is a tangent vector along some geodesic, okay, whichever geodesic we're solving for. So the point is that t mu k mu, okay, is a constant along the geodesic. Okay, so this, we're going to use this fact and the fact that we have 4 different killing vectors. We have R1, R2, R3, and T0. This T0 is not to be confused with this T mu. This T mu is a tangent vector to the curve. T0 is a time-like killing vector, okay, which is partial t. The particle does not follow partial t. Okay, this happens to be a killing vector and a tangent vector to a particle which is following a geodesic, which is just sitting in one place. Okay, in Minkowski space, that it happens to be a tangent vector. In this space, it is not. In this space, it is not the tangent vector to a geodesic. Okay. Okay, we're trying to solve for what these T mu's are. Okay. The other thing that we know is that T mu is also a constant along the geodesic, right? Because del t is 0, and so if I can take t outside and dot this into this, I get del t I'm suppressing the indices, but I hope you understand what I mean, right? Del t of t is 0. So this is t mu, and that is also a constant along the geodesic. So I have 4 constants along the geodesic. Okay, so let's write them out. Okay, so if the tangent to the geodesic in components is dx mu d lambda, these are the components of the tangent vector. So what is t mu? Well, let's define that as some epsilon, or we'll define minus of t mu as this epsilon. So this is minus g mu nu dx mu d lambda dx mu d lambda. Okay. Now we know that for massive particles, we can always choose lambda, which is an affine parameter, to be proper time. Okay, we can choose it to be the proper time. If we choose lambda to be the proper time, then d lambda square is just minus g mu nu dx mu dx mu. But in other words, epsilon is equal to 1. Okay, if we choose lambda to be the proper time. We have freedom to choose the affine parameter any way we like. We can parameterize the trajectory any way we like. And we have a freedom of affine reparameterizations. That is, if we have one affine parameter and I change the affine parameter to a tau plus b, then I would change, then it's still an affine parameter. So you can see that if I change my proper time to something like a tau plus b, epsilon would just scale by a constant. Okay, it would scale by 1 over a square. Okay. So we're basically just setting epsilon to 1, okay, by this choice of the affine parameter. For massless particles, okay, this is just 0 because the tangent vector is null. Okay, for massless particles, the tangent vectors basically have 0 norm. Okay, so this is 0. And for massive particles, the tangent vectors have negative norm, so that the whole thing is positive overall. Okay. So for massless particles, epsilon will be 0. That just means that you cannot interpret lambda as proper time. Okay, it just means that lambda is some parameter that describes the trajectory for a massless particle, but you can't think of it as proper time. Proper time for such a particle is always 0. Okay, now, so we understand one of the constants. Okay, one of the constants along the trajectory. So we said t mu, k mu is a constant. There are 4 such constants. Okay, one for each killing vector. And t mu is a constant. So we understood one of those constants. We understood what this epsilon is. Okay, it's 1 for a massive particle and 0 for a massless particle. Okay, now let's understand these other constants. Okay, this is basically 4 equations, one for each killing vector. What are killing vectors? Time translations. Okay, and then R1, R2, R3, which are rotations. Okay, rotational killing vectors. So what are these constants? Okay, so there's a deep analogy with classical mechanics here, right? When you have some symmetries, okay, when you have some symmetries, then for every continuous symmetry you have a conserved quantity. This is known as Noether's theorem. So time translation invariance is usually associated with energy conservation. Okay. Rotational symmetry about the x-axis is rotated with angular momentum about the x-axis being conserved. Rotational symmetry about the y-axis is associated with y component of angular momentum being conserved. Rotational symmetry about the z-axis is associated with the z component of angular momentum being conserved. Okay, so these conserved quantities should be equal to or have the interpretation of being energy Lx, Ly, and Lz, maybe up to some constant. Okay, maybe up to some constant. This is what you expect it to be. Okay, have you seen Noether's theorem before in your classical mechanics class? Okay. Okay, so so what you can do now is you can use the rotational symmetry, okay, to choose theta and phi coordinates, and you can choose the theta and phi coordinates in such a way that because of rotational symmetry, there will be some axis, okay, which I'll denote as the total angular momentum L, and L will be conserved along that axis, okay, and L is non-zero only along that axis, okay. So what that means is if the angular momentum is only along one axis, then the motion is going to be in a plane perpendicular to that axis. Okay, so what we're going to do is, without loss of generality, we'll choose our axis. We are free to choose what is our z-axis when we define polar coordinates. We'll choose our z-axis to be such that it's along the direction of angular momentum. Okay, and since the motion is in a plane, what that is going to do now is it's going to fix theta is equal to pi by 2. Okay, so theta is equal to pi by 2. So the entire motion of the particle will be in the plane theta is equal to pi by 2. Okay, with this choice. So we'll choose Lx. So with this choice, Lx is Ly is 0 and Lz is L. Okay, this is a freedom to choose your coordinate axis. So, so we've used two constants of motion, that is Lx and Ly. Both of them were set to 0 by a choice of our axis. So now we have this other L. Okay, so we've chosen theta is equal to pi by 2. So now we have two killing vectors left. Okay, which are basically the time-like killing vector, which is associated with time translations, which leads to energy conservation, and the killing vector associated with rotations about the in the xy plane, okay, which is rotations in phi, okay, or changing phi, where phi is the azimuthal angle. And this is so the killing vector is partial phi. Okay, I've written it in components as 0, 0, 0, 1. Okay, basically this is the coefficient of partial phi in this case. And this leads to conservation of angular momentum, right? So we define something which we call E, okay, and we define it as minus T0 mu, okay, where T0 mu is this killing vector times dx mu d lambda, where dx mu d lambda are the components of the tangent vector. So in components now I can write this. This is just 1, 0, 0, 0. Okay. Now remember that this is 1, 0, 0, 0 if I have an upper index here. If I lower the index, I have to lower it using the metric. Okay, and the 0, 0 component of the metric is minus 1 minus 2 gm by r. Okay, so that will give me 1 minus 2 gm by r. And the only component here then I choose is dx0 d lambda, which is dt d lambda. Okay, because I only have a non-zero component for t, the zeroth component of t0. Okay, so what I get when I take this product and sum over mu's is just this. Minus 1 minus 2 gm by r dt by d lambda.
So then the sign will be positive. The first metric component itself is negative. And it is minus 3.
Yeah, thanks. Okay, so let me recall whether the definition had a minus sign or not. Certainly, if we choose a minus sign in the definition, we get a plus sign. Okay, so I agree with that. Yeah, I think we do want a plus sign. So basically what we want is as lambda increases, t increases, we want a affine parameter to roughly increase in the direction of increasing time. This quantity is positive for r greater than 2 gm, okay, and therefore the energy we interpret as positive. Okay. So yes, so we do get an overall positive sign. Thank you. Okay, and then for L, okay, we define it with a plus sign, okay, and we define it as r3 mu dx mu d lambda. Okay, so again, this is killing vector dx times tangent vector. Okay, and again, the killing vector is 0, 0, 0, 1. Okay, and what we want is we want the 3, 3 component of the metric. We want G33. Okay, the 3, 3 component is the coefficient of d phi square. The coefficient of d phi square is r square sine square theta. Okay, so we get r square sine square theta. Okay. And dx mu d lambda, we only take the 3 component of this, which is d phi d lambda. Okay, so the net product is r square sine square theta d phi d lambda. But since we're working in the plane, right, where theta is pi by 2, then r square. So what we get is r square d phi by d lambda. We just get sine square theta is 1, and we just get L is r square d phi d lambda. Okay, so we have these two quantities which are conserved along the geodesic. So when the particle moves along the geodesic, these two quantities are conserved. Okay, what is the value of these two quantities? Well, that depends on the initial conditions that you set up your system with. Okay, but whatever it is, basically that's telling you that dt by d lambda times 1 minus 2 gm by r, that's a constant along the trajectory. Okay. Okay, now now a little bit about the interpretation of these constants. I'm just going to tell you the answer, and later we'll see why this makes sense. So for massless particles, E does have the interpretation of energy, but an important point is it has the interpretation not just of kinetic energy, but really the total energy of the particle. It's both the kinetic and the gravitational potential, what we would think of as the gravitational potential energy. It's the total energy of the particle that's conserved. Okay. And it's only conserved because you have a time-like killing vector. In general relativity, if you don't have a time-like killing vector, okay, your energy will not be conserved. So what that means is if you don't have a time-like killing vector, basically your metric components, let's say in general, are changing as a function of time. And so what that means is, let's say you're moving in a time-dependent background. Okay. So typically, when you think about, let's say, moving in a in a potential that's time varying, the energy of your particle changes. Okay, in response to that time variation of external time variation. And here we are basically considering the motion in a background metric. So we have a metric which is already set up for us, and our particle is moving through it. Okay, just following a geodesic. So we're asking, in that background metric, is energy conserved? And the answer is, it is conserved if you have a global time-like killing vector. If not, this is not going to be true. For the Schwarzschild solution, it is true. For Minkowski spacetime, it is true. Okay, but it's not true in general relativity that energy will be conserved. Okay, for a particle. For massive particles, okay, E is not the energy, but it's the energy per unit mass, okay, of the particle. It'll have the interpretation of being energy per unit mass. Okay, I'm not proving it here, I'm just telling you this. So similarly, L will be the angular momentum per unit mass for massive particles, okay, and L is just the limit of the angular momentum per unit mass for massless particles. Okay, it's the analogy of what you would define. So for example, if angular momentum is mv tangential times r, okay, L for L by m is v tangential times r. Okay, and you can define this for massless particles as well as massive particles. Okay, so now this is rather beautiful because now we have three quantities which are conserved along the trajectory. We have epsilon, okay, which is conserved. If we choose our parameter carefully, if we choose our affine parameter carefully, epsilon is either 1 or 0. Okay, 1 for massive particles, 0 for massless particles. We also have L, which is conserved, and E, which is conserved. So what that means is, along the trajectory, dE by d lambda is 0, dL by d lambda is 0, and d epsilon by d lambda is 0. Okay. Now, this is a consequence of symmetry. Okay, this symmetry is actually a property of the original geodesic equations that we wrote down. These 4 geodesic equations have that symmetry. It's harder to see, but the symmetry is there. Okay, this symmetry is described by the killing vectors. Okay, now what this means is basically these 4 equations guarantee for you that these quantities are conserved. Okay, they guarantee for you that dE by d lambda is 0, dL by d lambda is 0, dR by d epsilon by d lambda is 0. So instead of using those original 4 equations, we can rather use these 3 equations plus any one of those equations. Okay, and that gives us four new equations to work with. Okay, so this makes it rather simple. Okay. Yeah, sorry, I think I already made this comment. So you need a time-like killing vector to define the conserved energy of a test particle. Okay, in the Schwarzschild case, we happen to have that. Therefore, energy of a particle is conserved. This total energy of a particle is conserved. In a general spacetime background, which we have not seen examples of it yet. Okay, but for example, I've given you this one FRW example where the metric has a time dependence. So ds square is equal to minus dt square plus a square t times dx square plus dy square plus dz square. Okay, this describes an expanding universe. You can see that if a is increasing as a function of time, then the distance between 2 points, which are, let's say, this x and x plus dx, that actual distance increases by a factor of a of t. So this can be thought of as a time-dependent background. In this case, partial t will not be a killing vector, and in this case, energy of a particle will not be conserved. Okay, so this is an example of a case which is relevant when you study cosmology, where the energies of particles are not conserved. One way to understand this is in an expanding universe. If you have a wavelength of a photon, the wavelength of the photon gets stretched by the expansion of the universe, and so its energy, which would be hc by lambda, now becomes smaller because the wavelength of the photon gets stretched with the expansion of the universe. Okay, so in general relativity, depending on the space-time background that you're in, okay, energy may or may not be conserved. Okay, for conservation of energy, you need a global time-like killing vector. Okay, there is another definition of energy which is sometimes used in general relativity, which is supposing you have a particle with with moving along some trajectory, and p mu is the tangent vector to that trajectory. Okay. Then if you have another particle which happens to be at the same space-time point as that particle, and it has a 4 velocity u mu, then the energy can be defined, the energy as measured by this observer who is moving with velocity u mu, who happens to be at the same space-time point as that particle, where that particle is moving with a velocity 4 momentum p mu, that energy is minus p mu times u mu. Okay, this makes sense in special relativity, right? It's easy to understand why this is true in special relativity. So, for example, if you are at rest, then in your reference frame, u mu is 1, 0, 0, 0. Okay, and p mu is e 0, 0, p. Okay, if I take the dot product of these two using the metric convention that we have, we get a minus sign. We get minus e. Okay, and then sorry, even if I have px, py, pz, okay, I'll still get minus e, and that's why I take an overall minus sign. Okay. And this is what I'd interpret as the energy. Now, this energy, one thing about it is, one is it's measured locally. Okay, so you have to be present at the same space-time point to measure that energy. Okay, the second point is that this is not conserved in general relativity. Okay, for a free-falling particle. Okay, because this only measures the kinetic energy of a particle. This p mu is a tangent vector. This tangent vector is sort of describing the velocity, which is only describing the kinetic energy of the particle. So this is only measuring the kinetic energy of the particle. It's not measuring the gravitational potential energy. And if a particle is in free fall, its gravitational potential energy will change, its kinetic energy will also change. Okay, the total energy will be conserved if there's a global time like killing vector, but this kinetic energy will almost certainly not be conserved. Okay. Okay, so we've seen an example of this where, for example, if you take a photon coming out of a potential well, okay, so if it's deep in the potential well, let's say close to the surface of the Earth, it has some energy, or it has some frequency, which is, or it has some wavelength, which is hc by lambda. As it goes out of the potential well, okay, its energy decreases because the wavelength of the photon gets stretched, it gets redshifted. Okay, so the energy decreases, but this energy is only its kinetic energy. Okay, the kinetic energy has decreased. Okay, as it comes out of the potential well, we've seen this gravitational redshift effect in the weak field approximation. Okay, so why is the energy decreasing? Because this is only the kinetic energy of the photon. There is also potential energy. There's potential energy here, and by going over here, you have increased its potential energy and decreased its kinetic energy. Okay, or at least that's one way to interpret it. And again, if you have a global time like killing vector, then the total energy, kinetic plus potential, is conserved. Okay, so now what we can do is we will use these three equations. Okay, we'll use these three equations, and we'll use our dr by d lambda equation. Okay, so we'll use our dr by d lambda equation. We'll also maybe use the others, but at the end we can simplify. Okay, by using these conserved quantities. By using these conserved quantities, we can eliminate things like, okay, so for example, if I look at d by d lambda is 0, right? D by d lambda is 0 is basically, if I look at this equation and differentiate with respect to lambda, that tells me that d by d lambda of 1 minus 2 gm by r times dt by d lambda, this is 0. Okay, so what you can see is that now if I differentiate this, I'll get terms like d square t by d lambda square. So from the geodesic equations, which involves d square t by d lambda square, I can eliminate the d square t by d lambda square. Okay, similarly, you can do this for the other equations. And what you can get at the end is just a single equation which depends only on dr by d lambda and only on r. It doesn't depend on theta and phi. Okay, so you get one simple equation like this. So this equation is half dr by d lambda square plus something which we call v of r, okay, is equal to half e square, where e is what we had defined earlier. Okay, it's the conserved quantity along associated with the time-like killing vector. This v of r happens to be this. Okay, so it's quite a bit of messy algebra to derive it, but fairly straightforward. So what you get is half epsilon minus epsilon gm by r. Remember, epsilon is 1 for a massive particle, 0 for a massless particle, plus L square by 2R square minus GM L square by R cube. Okay. Now, if I want the trajectory of the particle, okay, I need to solve for R of lambda. Okay, so basically this is a differential equation in R, but this differential equation now involves those constants. It involves epsilon, L, and E. Okay, so those constants take care of the initial conditions, and I just have to solve for R as a function of lambda. Okay, but in principle, I also have to solve for, sorry. Yeah, in principle, I also have to solve for T of lambda and phi of lambda, but I can do that quite easily once I find R as a function of lambda. Okay, because all I have to do is use the conservation laws. So we've seen that dt by d lambda times 1 minus 2 gm by r is E, which means dt is E over 1 minus 2 gm by r times d lambda. If I've solved for r as a function of lambda, then it's quite easy to integrate this equation and get t as a function of lambda. I mean, at least in principle, I've put everything that depends on lambda on the right hand side of this equation. So just integrate and solve for t of lambda. And similarly, you can integrate and using the L conservation equation, you can get phi as a function of lambda. Okay, so it's fairly straightforward. So what we really have to do is just solve this equation for r as a function of lambda. Once we know r as a function of lambda, it's pretty easy to get t as a function of lambda and phi as a function of lambda. Okay, now let's make a comparison. Before we actually solve this equation, let's make a comparison with Newtonian gravity. Okay, so remember that first of all, this is an exact solution to Einstein's equations. Okay, exact geodesic solution. Okay, so we have an exact metric, and this is the exact geodesic that the particle follows. Okay, now let's compare this with our expectation in Newtonian gravity. In Newtonian gravity, you have kinetic energy. So let's say for a massive particle, kinetic energy plus potential energy is some constant. Okay, kinetic energy, we'll divide this entire equation by the mass of the particle. So kinetic energy per unit mass plus potential energy per unit mass is constant. The kinetic energy is half p square by 2m. Okay, or it's half mv square if you like, and we're now writing it as half v square. Okay, now the thing is, we're not writing v square in Cartesian coordinates, we're writing v square in polar coordinates. So we'll get half vr square plus if the motion is confined to a plane, okay, where v is only, let's say, in the phi direction and not in the theta direction, then what you will also get is v phi square or sorry or yeah, r phi dot square. Okay, r square phi dot square. Right. So this is what you get in the this is an additional term, but this is really the angular momentum. Okay, this is related to the angular momentum. Phi dot is the angular velocity. Okay, and r square omega square or m r square omega square is m square r square omega square is the angular momentum square. Okay, and so so this is, did you get that right? No, r omega is the tangential velocity. R omega is the tangential velocity. The angular momentum is mvt times r. mrvt. Okay, by the angular momentum law. Vt is r omega, so angular momentum is mr square omega. Okay, this is something that you're probably familiar with. So L by m. Okay, let me just define L as the angular momentum per unit mass. This is r square by r square omega. So this term in the potential energy now, if I write it as, I can write it as L square by r square, half L square by r square. Okay, so this phi dot square is omega square. Okay, and I stuck an r square in the numerator and denominator. R to the 4 omega square is L square. Okay, so half L square by r square. Okay, so this is the standard kinetic energy that you would expect in polar coordinates. The potential energy is minus gm by r, and this is a constant. Okay, so this is very similar now, looking to this expression that we have in gr. Okay, we have half dr by d lambda square. So we don't have lambda in t, we have lambda instead of t. But if you look at our expression for potential energy, we have well, this is a constant, so let's not worry about it. This is a constant. What we have for a massive particle is epsilon is 1 and we have minus gm by r. Okay, we have minus gm by r. And for the angular momentum part, we have this L square by 2r square plus L square by 2r square. This part is completely new. Okay, this is a new prediction of GR. Okay, which is not there in Newtonian gravity. Okay. So it's very similar to what we have in GR, except dr by dt is replaced by dr by d tau. Okay, and I'm using the affine parameter where lambda is equal to tau. And we have a new potential energy term. The new potential energy looks like this. So it's minus epsilon gm by r minus this extra piece, okay, gm L square by r cube. Okay, so the important point is that for massless particles, epsilon is 0. Okay, epsilon is 0. In Newtonian gravity, the analogous statement is saying massless particles don't feel the Newtonian gravitational field. Okay, they don't feel the Newtonian gravitational field. They do not experience the usual gravitational potential, but in general relativity, they will. Also, it's true that they do not experience this part of the potential. But in GR, they will definitely experience this part of the potential. They will experience a 1 by r cube type potential rather than a 1 by r potential. Okay, for massless particles. So massless particles will experience a minus gm L square by r cube part. Okay, for massive particles, if I set lambda is equal to tau, they will experience a correction to the Newtonian potential. So they have a minus gm by r part, okay, which is the standard Newtonian potential, but they have this extra correction, minus gm L square by r cube. So when is this correction important? This correction is important at, well, it depends on what the value of angular momentum is. Okay, but roughly speaking, when L square by r square is order 1, okay. Okay, that's where this correction becomes important. Then this term becomes comparable to this term. Okay, over here. Okay, so now typically what's done when you solve this in radial coordinates, what you do is you treat it as a 1D problem. Okay, you treat it as a 1D problem where I'm just solving as a function of r, and you absorb this part into like a 1D potential which depends on r. Okay, so you treat it as a 1D problem, and you define something called an effective potential V of r, which involves all these pieces now. So it has L square over 2r square minus gm by r minus gm L square by r cube. Okay, so you have a 1D potential. This part is there also in Newtonian gravity. This part is new. Okay, this is for massive particles. For massless particles, this term doesn't exist. Okay, this minus gm by r part is not there. And this part is the GR correction, minus gm L square by r cube. Okay, so now so for massless particles, it's this. Okay, it's the same thing without the minus gm by r. Okay, so this is the Newtonian part. Okay, and this is the GR correction. The Newtonian part is basically saying that it's a free particle, right? There's no standard potential. Okay, so let's look at the predictions of Newtonian theory first. Okay, so let's look at the predictions where we only keep the Newtonian piece. So it's only this for massless particles, and it's only this for massive particles. Okay, so let's look at the prediction for massless particles. For massless particles, imagine you're solving a 1D problem where I have motion in r. So my kinetic energy is this usual term, dr by d lambda square. Okay, but my potential energy is just a 1 by r square, where the coefficient of 1 by r square is positive. So 1 by r square looks like this. Okay, it's just falling as a function of r. And as I increase my angular momentum, let's say L is 1, 2, 3, 4 in some units, okay, my normalization of my potential energy increases. Okay, so it just goes up, okay, by some factor. So as my angular momentum is larger, okay, it basically goes up and it falls off as 1 by r. If my angular momentum is 0, then my potential energy is exactly 0. Okay, so this is what I have for a massless particle. For a massive particle, I have L square by 2r square minus gm by r. Okay, now at small r, this part will dominate. Okay, because 1 by r increases more rapidly than 1 by r square for small r. Okay, at sorry, did I get that right? No, the other way around. This term dominates for smaller. 1 by r square increases more rapidly as r gets smaller compared to this term. Okay, at small r. At large r, this term will dominate because 1 by r square will fall off faster. Okay, as I get to large r. So at very small r, I expect this to be again falling off as 1 by r square like this. Okay, 1 by r square, 1 by r square, 1 by r square. And it should go to infinity as r goes to 0, okay, because this term will dominate. But at large r, I expect this term to dominate, which is the minus gm by r. So I expect it to be of the form something like this, okay, which approaches, again, as r goes to infinity, this term approaches 0, so it should approach 0, okay, but it should approach it from the negative side. So what that means is, okay, so supposing L was equal to 0, then I would only have this minus gm by r, okay, this is a minus 1 by r type potential. Once I add the 1 over r square piece, then at near r is equal to 0, that gives me a correction which starts lifting the potential up, okay, and takes it to infinity. Okay, so what I will get is I will get a minima somewhere between, okay, r is 0 and r is infinity. I will get some minimum somewhere. That minimum will correspond to a v of r which is below the asymptotic value, which is 0. Okay, so where I've defined this at r is infinity, this is 0. Okay, as r goes to infinity, this goes to 0. This entire thing goes to 0. Okay, that's what we call the asymptotic value. Okay, so now look at these two potentials. Okay, imagine that you're solving a 1D problem where a particle is moving in this potential. Okay, and let's imagine what the solution would be. So first you'll have to prescribe what the energy of the particle is. Okay, so if the energy of the particle is this, and the particle starts at infinity and starts moving inwards, what you're effectively seeing is you're going to see a wall. Okay, you encounter a wall at some point, and then you bounce off of this wall and you just go back to infinity. Okay, so at least in R, this is what is happening. Okay, you bounce off the wall and you go back to infinity. This is what is happening for a mass in the massless case. In the massive case, okay, depending on your energy, if your energy is sufficiently large, again you'll bounce off this wall and go back to infinity. But if your energy is smaller, okay, let's say it's below 0, then you can exist in some state like this. These are the only places where your energy is greater than the potential energy. Okay, so this is your energy. Okay, if this is your energy, if your energy is negative in this case, then these are the only places where your energy is greater than this potential energy. Okay, so so if this is the potential energy, that is, you fix the angular momentum. Okay, if I fix L, and if I fix this energy, then this is the only range of R in which the state can exist. So this is what is called a bound state. Okay, so for a massive particle, this minimum of the potential, we can work out where the minimum of the potential is. So we just take V of R is L square by 2R square minus Gm by R, differentiate with respect to R. We get minus L square by R cube plus Gm by R square. Okay, and we can write that as Gm R minus L square by R cube. So what we get is we get a solution which is R critical is L square by Gm, and this is a minimum. Okay, this is going to be a minimum. Okay, so the point is that this point, which is the minimum, actually implies that R is equal to constant. Okay, and this point, since it's a minimum, will actually be a stable orbit. Okay, so it will be stable and it will be a circular orbit because R will be a constant. Okay, at this minimum for massive particles. So for massive particles, if your energy is finely tuned for a given angular momentum such that you are at the minimum of this potential, then you will have an exactly circular orbit around this minus Gm by R type potential. Right? This is something that you're very familiar with from in high school physics. Right? For a massless particle, okay, let's understand Newtonian gravity for a massless particle. What we have is essentially this equation. Okay, now this is a bit strange, but basically what we're saying is we're sort of in the approximation where we're writing v square as a constant. Okay, for a massless particle, and we've just written it in polar coordinates. Okay, what that really means is the particle is moving along a straight line. V is a constant, so it's just moving in one direction. But how do we interpret it in terms of this 1D potential? Okay, we got a 1D potential. Well, imagine that the particle is moving along a straight line, but now you've given it some angular momentum. What that angular momentum means is if this is my origin, then it has some impact parameter, some minimum r near this origin through which it passes. Okay, so it passes over here. So what is going to happen is the radius is initially very large. Okay, then the radius approaches a minimum radius, and then the radius again increases. Okay, so in the 1D problem, that looked like, as r is a function of lambda, it just looked like it came in, r decreased, hit some critical value, and then it bounced back. Okay, that's what it looks like. But really, what we have not done is we've not solved for the angle as a function of lambda. So we don't really know what is happening in the angle. If we had solved the angle equation, we would have found that it's a straight line motion, okay, in Cartesian coordinates. So for the massless particle, dr by d lambda first decreases and then it increases, okay. Okay, so basically now what we have to do is, now let's look back again at massive particles. So for massive particles, we said that there's a stable minimum, okay, and the stable minimum would give rise to circular orbits. But you can also have energies which are larger than this stable minimum, right? This energy has to be finely tuned so that you're sitting exactly at that critical point where you have a circular orbit. If your energy is larger than this minimum energy, okay, then at least in R, you are going to undergo oscillations about this minimum. Okay, so your radius is going to increase and decrease, increase and decrease. Okay, but that doesn't mean your trajectory. Okay, so your stable orbit looks like this. That is, if your energy is finely tuned so that you're sitting right at this minimum. Okay, R will be a constant and theta will change. Okay, in fact, you can show that theta dot will be a constant. Okay, in this case. Okay, that's because angular momentum is conserved, right? Angular momentum is r squared times theta dot. Okay, so this is conserved, so theta dot is constant. So you'll just travel at a constant rate. You'll go around this circle. However, if you have some energy which is above this minimum value, then you're still in a bound state. R will oscillate as a function of time, but that doesn't mean that you will do something like this. Okay, this is not what you're going to do because we've not solved the theta equation yet. In theta, if you solve it, you will find that you get an elliptical orbit. Okay, the orbit will be an ellipse. So in this ellipse, if I look at it, R is first large, then R decreases, R approaches a minimum, then R starts increasing again. Okay, so in R, it's undergoing an oscillation, dr by d lambda. It's an asymmetric oscillation. Okay, one side is larger than the other, but that's because this potential is asymmetric. Okay, the potential is asymmetric on one side and different on another. So you'll go between these turning points. Okay, where the energy is equal to the potential energy. At the turning point, you have the maximum radius and the minimum radius. Okay, and you basically oscillate. Okay, you'll have a slightly larger R and at maximum and a slightly smaller R than RC at the minimum. Okay, so this will be your motion in R. The theta motion is more or the phi motion is more complicated. You have to work it out. Okay, but if you've taken an advanced statistical mechanics course, you would have seen that you get elliptical orbits. Okay, and that's also what you know from Kepler's laws, that you get elliptical motion. Okay, now for massive particles, okay, if we look at the GR equation, yeah, okay, so we had half epsilon minus epsilon gm by r, this epsilon was 1, okay, plus L square by 2r square minus gm L square by r cube. So for and that whole thing, that whole expression for energy was equal to half E square. Okay, that half dr by d lambda square plus all of that was equal to half E square. So the constant half E square minus half epsilon, this is what we actually think of as the energy in Newtonian gravity. Okay, this is the piece that we think of as the energy in Newtonian gravity. In GR, you have to define the absolute reference level. Okay, so the absolute reference level is fixed. Okay, so this gives us some energy. So if E is greater than 1, okay, so this quantity now is, if epsilon is equal to 1, then what we're saying is if E is greater than 1, okay, if E is greater than 1, then the total energy, okay, that is this entire thing is positive, okay, which means that your energy is greater than 0. Okay, this value, what we're calling energy, is half E square minus half epsilon in GR. Okay, so in other words, if I call this as energy, okay, this energy should be greater than 0 for me to have scattering states. I need E less than 0 to have bound states. Okay, to have bound states. Okay, so in terms of capital E, if E is greater than 1, I have unbound states. If E is less than 1, then I have bound states. Okay. Okay. So if E is greater than 1, then you will have these unbound orbits. Okay. So in Newtonian gravity, these are like parabolas or hyperbolas where you come in, okay, and kind of escape off to infinity. Okay. Okay, now that we understand what happens in Newtonian gravity, let's contrast with what happens in general relativity. So in general relativity, the main thing is you have this extra term, minus gm L square by r cube. Okay, and you have to compare this with minus gm by r. Okay, for r square much greater than L square, as long as the particle is staying at some r which is very large, this extra p should not be very important. Okay, which means the behavior should approximately behave like Newtonian gravity. Okay, we should recover Newtonian behavior as large r. So these terms actually dominate as r goes to infinity, but this term is actually now going to be the most dominant term as r goes to 0. Okay, so as you get to small r, this gr correction is actually going to be the most important term. Okay, that's something that we anticipated in the weak field limit also, right? As you get to lower r, you expect the gr corrections to become important. Now, what does a minus 1 by r cube potential look like? Well, a minus 1 by r cube looks like this. Okay, it very sharply decreases, okay, to 0 as r gets small, and then it increases as r goes to 0. As r goes to infinity, this goes to 0. Okay, but it's always less negative. Okay, so it always stays here. So now what we do is we have to add such a term. Okay, we have to add such a term to our Newtonian potentials, to our 1D Newtonian potentials. So we have this 1D Newtonian potential and this 1D Newtonian potential, and we have to add this term. The effect of this term is going to be most important at small values of r. Okay, which means at small values of r, the potential is not going to turn up, rather it's going to turn down. Okay, and again here also in the massive particle case, it's not, the potential is not going to turn up at r is equal to 0, it's going to turn down, okay, towards minus infinity. So the potential is going to look like this. Okay, for massless particles, you will get this. Okay, it's that same barrier that we saw before, which goes as 1 by r square here. Okay, but here it's going to fall off as minus 1 by r cube. Okay, in this region. For massive particles, it's a little more complicated because you have three terms now. You have the minus 1 by r potential, Newtonian gravitational potential. You have the 1 by r square from the angular momentum, and you have the 1 by r cube, minus 1 by r cube from gr. Okay, at very small r, you know it's going to be the gr effect. You'll always turn down to v is minus infinity. At very large r, you know it will be the Newtonian gravitational potential, which will be minus gm by r. At intermediate r, it is possible that in some regimes of parameters for L and M, certain values, that the 1 by r square, L by square by r square could become important, okay, in the middle. Okay, it turns out that the L square by 2r square is important for L greater than something like 4. Okay, L greater than or equal to 4, or actually root 12, as we'll show. Okay, for L greater than root 12 GM, it turns out that the 1 by r square behavior is important. Okay, so roughly speaking, you will directly transition from 1 by r cube minus 1 by r cube to minus 1 by r for L less than or equal to root 12 GM. Okay, you will roughly just directly make this transition. For L greater than root 12 GM, you will also have this intermediate behavior where you fall off as 1 by r square. Okay, where you have that barrier. Okay, so let's see how this 1 by root 12 comes about. Okay, so let's take our full potential and we'll try to locate the extrema of this potential. Okay, basically what we're going to argue is that if L is greater than root 12 GM, you will have a maxima and a minima, okay, of the potential. If L is less than root 12 GM, then you will not have a maxima or a minima. I mean, the maxima and minima will only be at infinity or at 0. Okay, there will be no maxima or minima in between. Okay, so let's work that out. So let's work out dV by dr. So it's minus L square by r cube plus epsilon gm by r square plus 3 gm L square by r4. Okay, this is for massive particles. We've taken epsilon as 1. Okay, but I'll just write it in. So for massive particles, we have, if I just rewrite this equation by multiplying throughout by r to the 4, okay, then this term has an r square, which is gm r square. This term is linear in r, it's minus L square r, and this term is a constant, it's 3 gm L square. So this is just a quadratic equation. Okay, the quadratic equation which tells me where the extrema are. If the quadratic equation has roots, which means the discriminant is positive, okay, that means you have a maxima and a minima. If the quadratic equation is doesn't have roots, then you don't have a maxima and a minima. Okay, so that will correspond to these cases that we've seen here, where you don't have a maxima and a minima, versus later when at large values of L you develop a maxima and a minima. Okay, for massless particles this epsilon is 0. Okay, and what will happen is that you will only have one solution. Okay, which is R is equal to 3 gm. Okay, RC is 3 gm. This will correspond to a maxima. Okay, this is a local maxima. This local maxima will be an unstable orbit. Okay, you can orbit at that location. Okay, if your energy is exactly this value, but it will be unstable, which means any small perturbation and the massless particle will no longer orbit. It will shoot off to infinity. Okay, this behavior is completely unexpected from Newtonian gravity. Newtonian gravity, light will move in a straight line. In GR, light can orbit a black hole, even though it's an unstable orbit. In principle, this is a solution. Okay, so light can just orbit well, we're not even saying this is a black hole. This is just some spherically symmetric potential. Okay. Okay, so even around a neutron star, for example, you could orbit. Okay, provided you're sufficiently close. Remember that 3 gm is a very small number, right? For the mass of the sun, okay, 2 gm, which was the Schwarzschild radius, was 3 kilometers. Okay, so 3 gm is 1.5 times 3 kilometers, which is 4.5 kilometers. So if you have an object which is the mass of the sun, it needs to be compressed to at least within 4.5 kilometers for light to orbit it. Okay, so it needs to be ultra compact for light to orbit it. Okay, that can only happen for a neutron star or a black hole. Okay, for massive particles, okay, you can solve this quadratic equation, and if you solve the quadratic equation, you will get something like this. You will get L square plus minus square root L to the 4 minus 12 gm square L square by 2 gm. Okay, these are the solutions. Okay, there are two values, but in order for solutions to exist, this discriminant must be positive, which means L square is greater than 12 gm square. Okay, that's exactly where I told you this critical condition is going to come from, where at a critical value of L, you will develop a maximum and a minimum. Okay, somewhere in the middle. The maximum will correspond to unstable orbits. The minimum will correspond to stable circular orbits. Okay, so RC will be equal to, if you simplify this, okay, you'll get something like this. And if L is greater than or equal to 12 gm, root 12 gm, you get two circular orbits. One is stable and one is unstable. Okay, you can work out where these stable orbits are for very large L. Okay, so you can work out where that stable orbit is, or where the stable and the unstable orbit are. For very large L, you can show that the stable orbit moves to L square by gm, and the unstable orbit moves to 3 gm. Okay, so the unstable orbit, if I'm at very large angular momentum for the massive particles, the unstable orbit is exactly at the location where the photons would orbit. Okay, photons would be in their unstable orbit. On the other hand, the stable orbit is exactly where it would be for the Newtonian gravitational potential. For the Newtonian gravitational potential, we found a stable orbit at this location, okay, at L square by gm. That's also something that you expect. At large L, you're at large distances. At large distances, you're basically just dominated by the Newtonian gravitational potential. So the circular orbit or the potential should look exactly like the Newtonian gravitational potential. Okay. But in general, at intermediate values of L, not very, very large L. So L small enough that you're orbiting relatively close to this object, okay, or this potential, you will have sort of this basin of minima. Okay, you'll have this basin of minima over here. But you'll note something interesting, right? Which is, if you have angular momentum, even if you have angular momentum, nothing is preventing you from going all the way to R is equal to 0 if you have sufficient energy. Okay, in the Newtonian case, there's always a barrier. Okay, if you have sufficient energy, there's always a barrier which prevents you from going towards R is equal to 0. Okay, but what you see is that even if you have very large angular momentum, okay, even if you have very large angular momentum in GR, okay, it's possible that you can go towards R is equal to 0. Okay, even at very large energies. However, it is possible that if your energy is sufficiently small, you can exist in these minima, you can exist in this trapped minima. Okay, so you can have circular orbits or you can have non-circular orbits, okay, where you're kind of oscillating in R, okay. Okay, so in addition to the circular orbits, which are at the minimum for the massive particle, you will also have unbound orbits, and you'll have bound orbits which are not circular. But in general, unlike Newtonian gravity, since the potential is not just 1 by r minus 1 by r cube, sorry, it's not just 1 by r, but you also have this 1 by r cube, the orbit is more complicated to solve for. It's not necessarily going to be these conic sections which are hyperbolas, parabolas, or ellipses. It's a more complicated orbit. In fact, you may not be able to derive an analytic expression for that orbit, okay, an exact analytic expression. However, I mean, to actually show this, you also need to solve the d phi by d lambda equation, okay, to figure out what the actual orbit is. Okay, we're not doing that right now. Okay, so if you, in summary, okay, in GR, if I look at the stable orbits of massive particles, okay, you can show that stable orbits will exist between 6 GM and infinity. Okay, for massive particles, the stable orbits are between 6 GM and infinity. Okay, this is the sorry, I forgot to mention something. Okay, so now basically there is a critical value of L, which is L is equal to root 12 GM. At root 12 GM, something interesting happens. The maxima and the minima merge with each other. The discriminant is 0. So these two solutions to the quadratic equation that we found, those merge with each other. So that is the innermost possible stable circular orbit. Okay, for a massive particle, it cannot go in any further than that. Okay, you can still have this unstable orbit at 3 GM. Okay, for large angular momentum. But for this critical value of LC is equal to root 12 GM, okay, there the maxima and the minimum merge, and so you have this. It actually becomes a saddle point. Okay, that's basically the limit of your innermost stable circular orbit. So for 6 GM is the smallest possible radius of the stable circular orbit. Okay, and so you have stable circular orbits between 6 GM and infinity, and you have unstable orbits between 3 GM and 6 GM. Okay, so roughly speaking, your potential looks like this. This is R plus, this is R minus. R minus can start from 3 GM. When R minus is at 3 GM, R plus is at infinity. As R minus, as you increase the angular momentum, as you decrease the angular momentum, R minus moves out to 6 GM. Okay, and R plus moves into 6 GM. Okay, and they meet when the angular momentum hits this critical value of square root 12 GM. Okay, for higher angular momentum, for lower angular momentum, okay, you do not have a stable minimum anymore. Okay, of the potential. Okay, which means that for any energy, okay, the particles will fall in towards R is equal to 0. Okay. So let's understand what that means. So what we're saying now is if L is less than this critical value, okay, the potential looks like this. There's no maximum or minimum. This is for massive particles. Okay, it's minus 1 by R cube here. It's 1 by R here. Okay, and now what we're saying is no matter what energy you start with this energy, you will approach here. If you start with a lower energy, okay, then you imagine that you started here, you will still fall in, okay, towards R is equal to 0. Okay, there's no barrier, okay, which will prevent you from getting there. Okay. Okay. Now all of this is for particles moving only under the influence of gravity. That is geodesic motion. That is particles which are in free fall in gravity. Okay. So particles with other forces, for example, if you have a rocket ship which is accelerating, these other particles can certainly dip below. I mean, they don't have to stay at this stable circular orbit. They can go to lower R. They can come out to larger R. Basically, the acceleration is you're supplying them with an additional source of energy, right? You're converting chemical energy into the energy of the rocket, okay? Into the kinetic energy or potential energy of the rocket. So these other particles can dip below 3 GM. They don't have to stay in bound orbits. They can go below 3 GM. They can come out above 3 GM. There's no problem, okay? But you have to accelerate for that to happen. However, what we'll see is if R goes below 2 GM, okay, then you'll see that nothing can escape. It doesn't matter how hard you accelerate, you will just fall in. You will keep going towards r is equal to 0. You will go to smaller and smaller r. So if r is less than 2 gm, we'll see that nothing can escape. Okay, and so if an object is ultra compact, okay, it's confined to within the Schwarzschild radius, then nothing can escape, and that is called a black hole. Not even light, nothing can escape. Okay, no matter how hard you try to accelerate, you will not be able to escape from that point. Okay. Okay. Now, so this is the next thing that we're going to look into. This is probably the last topic we'll cover in the course. Okay, which is the idea of a black hole. Now, one comment here before we move on to discussing black holes is now we have this exact potential, okay, that you see in the Schwarzschild case in general relativity. What I'm not going to do is you can now work out, let's say, what are the orbits of the planets if you have this extra -1 by r cube. Okay, and what you can show is that it leads to precession of the perihelion. If you have an elliptical orbit, if I'm at sufficiently large r, then I can treat this gm by r cube as a small perturbation to the potential. Okay, and certainly for Mercury, right, the r, even though it's close to the sun, okay, it still has a radius which is much greater than the Schwarzschild radius of the sun, which is only 3 kilometers. Okay, so even though you're very close to the sun, r is still much greater than the Schwarzschild radius. So you can still treat this as a small perturbation, okay, to Mercury's elliptical orbit, and you can show that there's a precession of Mercury's elliptical orbit. What you need to do is also solve the d phi by d lambda equation, right? You need to figure out how it goes around the sun. Okay, how is the angle changing as I go around the sun? And this is done in section 5.5 of Carroll, and it works out the correction to the precession of the perihelion of Mercury. Okay, this is something I'm not going to cover. Okay, so now let's move on to the fascinating question of what happens, okay, when the object is so compact that you don't encounter it till r is equal to 2 gm. Okay, what happens when r becomes less than 2 gm? Okay, so now the object is ultra compact. So the Schwarzschild solution is valid as long as you're in vacuum, which means if I've not encountered anything, any material, okay, of the object till r is equal to 2 gm, the Schwarzschild solution is valid as long as I have spherical symmetry. So now let's imagine that we're doing an experiment. Okay, let's dive in, okay, to this region where r is equal to 2 gm. This is a thought experiment. We're not actually going to do it. In fact, let's be so scared to do this experiment that we won't actually dive in. We'll send a roommate inside, and we'll wait on the outside of the black hole. Okay, so so this is us or you. Okay, you wait over here. Okay, and you are at very large r. Okay, and your roommate. Okay, so this is time. Okay, this is your time coordinate. This is the r is equal to 2 gm. Okay, this is the critical value. And let's be kind to our roommate and not just throw them in. Okay, let's give them a rocket ship. Okay, so that they can accelerate and stay hovering above this surface. Okay, so if they hover, they can stay at any radius, right? Because as long as they're supplying energy, you can stay at whatever radius you like. Okay, so they have a rocket ship and they're able to stay at some particular r. This r can be less than the innermost stable circular orbit, which is at 6 gm. Okay, so they can be much closer, okay, to the surface of this black hole. So now imagine that you have your roommate at two different times, r1 and r2, okay, where this is your t coordinate. And now you're giving your roommate instructions, okay, which is as you get into the black hole, you give them a clock. Okay, you've checked your clocks. Your clocks are in sync when your roommate is near you. You've checked your clocks. You say, okay, you're all set. Go into the black hole. Here's a flashlight. Okay. What I want you to do is every 10 seconds on your clock, okay, you flash once. Okay, just to tell me you're okay. Okay. And then the roommate is a little worried. He's like, are you saying the things are not going to be okay? But okay, let's not worry about that. You just go there and like every 10 seconds, okay, just keep sending me a signal every 10 seconds, okay. And so you pat him on the back, pay him around on the back, send her into the black hole, okay, on this rocket ship. So now your roommate is here and they count off 10 seconds on their clock, okay. So that's a time delta t tau for your roommate, okay. They count off 10 seconds and then they send a light signal towards you. Okay, this light signal will follow geodesic, okay, it will reach you. Okay, 10 seconds later, they send a light signal which reaches you. Okay, these light signals will reach you at a time delta tau for you. Okay, these times will not be the same because of time dilation. Okay, we've already seen the time dilation effect. So time, the clock near a black hole, if it ticks off 1 second, okay, the time for you would have ticked off a very large amount, okay, because your roommate is very deep in the gravitational potential, okay. So for you, it would have ticked off a very large time amount. So even though you told them every 10 seconds on your clock, you send me a signal, these signals will now reach you, okay, if they're at a fixed R, these signals will reach you maybe 20 seconds apart. If they go deeper in R, these signals will reach you 1 minute apart. Okay, if they go even deeper, they'll reach you hours apart or even days apart or even years apart. Okay, it depends on how deep they go in the gravitational potential. Okay, now the space-time is now the important point is the space-time is static. Okay, so the time it takes along the path, okay, to reach you is the same for each of the. It doesn't matter when the your roommate sends it. This time taken is always the same. So you only have to worry about the time interval between, okay, between two flashes. Okay, and that changes. I mean, that is a different time as measured by your roommate as versus as measured by you. Okay. Okay. So the light signal sent at R1 and R2 take the same time to reach you. Okay. So now let's suppose, okay, now we want to compare this with your t coordinate. Okay, we're using t coordinates. So for you, delta tau, okay, will be, so if you just look at your ds square is minus 1 minus 2 gm by r, okay, dt square, plus 1 minus 2 gm by r inverse dr square. Okay, remember this is an exact solution. Okay, if you are at fixed r, okay, your r coordinate is not changing, your theta coordinate is not changing, your phi coordinate is not changing. All of these other terms are unimportant. Okay, the time interval and this ds square is just therefore going to be the proper time minus of the proper time that is elapsed for you. Okay, if you are at large r, d tau is equal to dt. Okay, basically the asymptotic observer dt is the proper time. Okay, the asymptotic observer is sitting far away. So for you, delta t is a good measure of the time that is elapsing on your clock. Okay, for your roommate, however, dt, okay, is 1 minus 2 gm by r times delta t. Okay, and this we have already seen in the weak field approximation. This is exactly what you get also in the weak field approximation. Okay, and so what it tells you is that if I take delta tau r by delta tau y, that is the time elapsed on your roommate's clock versus the time elapsed on your clock, this is 1 minus 2 gm by r. Okay. In other words, if you tell your roommate to send a signal every delta tau r, so delta tau r is fixed, so let's say every 1 second, then delta tau y, okay, will be, this is the time elapsed on your clock between two signals. Sorry, this is 1. This is equal to delta tau of your roommate by 1 minus 2 gm by r. Okay, if r is large, that is if your roommate is just starting out on his journey, not gone close to the black hole, r is large and your clocks are ticking at exactly the same rate. As r gets smaller, okay, as r gets close to 2 gm, this becomes close to 0, okay, and delta tau u becomes closer to infinity. Okay, so in fact, even for 1 second elapsed on their clock, if they're just very, very close to this 2 gm, the time between two signals is going to approach infinity. Okay, so you might be wondering what happened to your roommate. Okay, but if you wait long enough, you will still see a signal from them. Okay, no matter how long you wait, you will still see some signal from them. Okay, as long as they're at finite distance from 2 gm. So if you tell your roommate to send you a signal every 1 second on his or her clock, you will still receive the signals. They will just be further and further apart on your clock, the closer and closer the roommate is to the black hole. Okay, so the closer your roommate gets, further apart in time the signals that reach you. The other thing that we've seen, which I'm not going to reproduce here, is that the light signals get more and more redshifted. Okay, so even though you might have sent them a green laser or a UV laser, okay, the signals will get redshifted. So the closer they are, what you will see is if you send them with UV light, the closer they are, first the light will appear to be visible light. Then as they get closer, it will become infrared light. Then as they get even closer, it will become radio wavelengths. And then it will become so long that you don't even have a detector which can detect it. Okay, so it's basically going to drop out of the frequency range of any detector that we build. Okay. And now the critical question is, what if your roommate allows themselves to free fall? Okay, what if they now allow themselves to free fall into the black hole? That is, if they allow themselves to get to r less than 2 gm. So instead of hovering now, eventually they run out of fuel. Okay, they curse you for sending them there. Their rocket ship just falls in. Okay, they're now following geodesic motion. Okay, we've seen that there's nothing to prevent free fall at that point. Okay, our coordinate system is not valid, so our metric is not valid, but your roommate falling in will experience something, right? We want to learn what would they experience. Okay, as far as you are concerned, you're sitting comfortably. Their journey has ended. You will never hear from them again. Okay, beyond this point. Okay, they as long as they had fuel and they were hovering above RS2GM, those signals were reaching you. Okay, and those signals will continue reaching you. Okay, even if you wait an infinitely long time. But once they cross 2GM, what we'll see is that those signals will never reach us. You will never get information about the fact that they have crossed that R is equal to 2GM. Okay, so you will continue receiving signals. These signals are further and further apart. It will seem to you like they're getting closer and closer to R is equal to 2GM. But according to you, sitting very far away, your roommate has never quite reached R is 2GM. You have to wait forever to get that last signal from them near R is equal to 2GM. But your roommate is experiencing something quite different. Okay, at R is equal to 2GM, they're not going to experience anything drastic. They will just continue on their motion towards smaller R. Okay, so that's what we're going to try to do next, which is we will now follow your roommate, okay, through this event horizon of the black hole. Okay, so this region of no return, the point of no return at R is equal to 2GM, we will show that it's a point of no return first. Okay, we'll show that you cannot come back out from that point. Okay, so we have a couple of minutes, so I'm just going to go through the basic argument, and then we'll continue this in the next class. Okay, any questions at this one? Okay, so we have seen that R is equal to 2GM is a coordinate singularity. Okay, and we also discussed, okay, although I didn't quite show it, is that if you compute any curvature quantity in the limit R goes to 2GM, your curvature quantities are all finite. Okay, so that indicates even though your metric sort of seems to be breaking down, there's nothing physically wrong about the point R is equal to 2GM. It's maybe these coordinates don't cover it. Okay, just like we've seen with Rentala coordinates. Rentala coordinates don't cover the entire space. Okay, so our coordinate patch is only valid for R greater than 2GM. Okay, and we've understood the trajectories. We've understood that you have these bound state orbits, you have these unbound orbits. You've even understood what your roommate will do up till the point that they fall into the black hole. Okay, but what we do not understand is what is happening for R less than 2GM. Okay, you certainly don't expect that the manifold ends. Okay, because the curvature there's nothing wrong with the curvature. So your roommate will experience something not very unusual. Okay, at that point, they'll experience large gravity, there are large tidal forces. Okay, but nothing very unusual other than that. Okay, in fact, if the black hole is sufficiently large, even the tidal forces will not be that large. Okay, when they get close, because yeah, okay. Let me not get into those details. Okay, so as R goes to 2GM, what we'd like to do is, can we somehow extend our coordinates, maybe by making a change of coordinates, so that our coordinates will cover the region below R is 2GM without encountering this singularity or this degeneracy in our metric. Okay, so let's recall what we did for Rindler observers. So Rindler observers had these coordinates rho and eta. Rho parameterized the hyperbola. Rho is equal to 0 was the asymptotic hyperbola, where the hyperbola basically became these light curves. Okay, rho is equal to 0 was strictly not part of our Rindler patch. Okay, rho greater than 0 was part of our Rindler patch. So you had this rho and you had eta. Okay, so eta 1, eta 2, and so on. And in Rindler coordinates, the metric was minus rho square d eta square plus d rho square plus dy square plus dz square. And the Rindler patch was only valid for 0 rho less than infinity, minus infinity less than eta less than infinity. Now let's imagine that you ask the reverse question. Okay, we started with Minkowski coordinates t, x, y, z, and we found the Rindler coordinates. But what if you only knew Rindler coordinates? What if you only knew that there was rho t, x, y, z? You only had this metric. How would you discover, okay, the t, x, y, z coordinates? Okay, how would you discover the t, x, y, z coordinates? In other words, how would you discover that your coordinate patch is incomplete? Okay, how would you discover that, right? If you didn't already know that there's a t, x, y, z. So that is, if you only had rho x, y, z, Okay. Well, one thing you could have done is just say, let me be clever and somehow guess that there is such a coordinate transformation. Okay. So let me somehow guess that there is a coordinate transformation. X is equal to rho cos theta, t is equal to rho sin theta. In your coordinates, rho eta only cover the Rentala patch, which means that this dictionary is only valid in the region where, first of all, x is positive and mod x is less than t. Okay, that is in the Rentala patch. Okay, and now what you're really guessing is that somehow, even though my coordinates in my Rentala patch only extend between 0 and infinity, this new x coordinate and t coordinate, I will now extend them beyond, okay, from minus infinity to infinity. Okay, and and why can you do that? Well, if I convert my metric, okay, or my space-time line element from this to these x, y, z, t coordinates, I will get something that's very regular. Okay, it doesn't have any singularities, and this seems like it can be extended for x, large t, large y, large z. So if I somehow guessed the correct dictionary that somehow puts the metric in a very nice form like this, okay, then I could guess that I can extend my coordinates. Okay, that is, even though the t, x, y, z under my dictionary are only valid in this range, okay, now that I have this dictionary and I find that the metric is regular, let me just extend them to t is plus minus infinity, x is plus minus infinity without any restriction. Okay, and I'll cover the whole space. Now you encounter no singularity or degeneracies in the metric. The problem with trying to do this with rho and eta is that if I try to extend rho to rho less than 0, I immediately encounter the singularity. Okay, that is, my metric has a 0 eigenvalue. Okay, it's a degeneracy rather. Okay, so the main point of doing this is that I had to somehow magically guess this coordinate transformation from Rentala to Cartesian coordinates. Okay, but what if you can't guess so easily? How do you discover other regions of space-time? Supposing I don't know the guess, right? I mean, of course, if I give you the right answer, you can check it. But if I don't know how to guess, how will you discover other regions of space-time? So imagine asking this question physically now. Okay, imagine that you and a bunch of friends were Rentala observers. Okay, how would you discover that there's a region of space-time which is beyond you? Okay, beyond your existence. Okay, or beyond your friends. Okay. The answer is very obvious. You stop accelerating. Why are you trying so hard, right? Just stop accelerating in free fall. If you're in free fall, you'll follow geodesic. Okay, geodesic motion is so the answer is you just follow geodesic. Okay, that is, you stop resisting, stop trying to accelerate so hard, and just go with the flow. Okay, that is, you follow geodesic. So, for example, if this was you, okay, accelerating like a good Rentala observer, okay, following rho is equal to constant. Okay, if you now change your trajectory, so instead of now at this point, instead of accelerating, you either start following a time-like geodesic, which would be something like this or something like this, or you follow a null geodesic if you're massless or send out a light signal. Okay, the null geodesic would follow something like this. Or if you could somehow send out a space-like geodesic. Now, a space-like geodesic, obviously, you can't physically do it. Okay, but mathematically, you can imagine a space-like geodesic extending beyond your coordinates. Okay. So you can follow a geodesic, and obviously no physical observer can follow a space-like geodesic. Okay, but as a mathematical step, okay, if I want to discover the full space-time, basically I just follow geodesics. Okay, I just follow geodesics to wherever they lead me. Okay, so I don't worry about what my coordinates are. Rather, I follow geodesics because geodesics are physical things on the manifold. Okay, they don't care about what coordinates you're using. Okay, and now what you can do is, if your Rentala patch is, let's say, this region 1, okay, which is this region here, and if I start with some point here, if I follow a future null geodesic, okay, that is a null geodesic, where the tangent vector is a null vector, then I would discover this region. This is region 2. Okay, so any null geodesic will at most take me to region 2. Okay, but it will never take me to region 4 or region 3, which is in this region or this region. Okay, so a future null geodesic will take me into region 2. Okay, a space-like geodesic, okay, will just go this way, and it will take me into region 4. Okay, but if I want to discover region 3, then I also need something like this past null geodesics. Okay, past null geodesics, which will take me into this region. Okay, so either following a geodesic, either a null geodesic into the future or into the past, or following these space-like geodesics, I can now discover other regions of the space-time. Okay, So rather than be confined to the coordinate system that you're using, it's better to talk about something physical. Physical in the sense that once I have a metric, let me talk about the geodesics of that metric. The geodesics will help me figure out the rest of the space-time. Okay, so then I don't have to worry about the inadequacy of my coordinate system. Okay, so in the next class, what we'll do is we will go back to the Schwarzschild metric, and we will follow geodesics. Okay, we'll follow null geodesics, we'll follow space-like geodesics, and we'll try to discover the rest of the space-time. This rest of the space-time will take us beyond this region r is equal to 0, and it'll take us on this exciting journey with our roommate if we had been brave enough to follow. Okay, so that's what we're going to do next time, which is we'll follow the roommate into the black hole. Okay, let's stop here. Any questions? Yeah.
So can we be sure that this even works? Because like experimentally we are saying that anything that goes beyond 2 here and we never hear back from them again. So experimentally it's not possible to determine what's happening.
Yeah, so if you want to do an experiment, you need to go follow your roommate into the black hole. Otherwise, as far as you are concerned, you will never know anything about the interior of the black hole. Okay, I should point out that this is what we call a classical theory. Okay, the remarkable discovery of Stephen Hawking in the 1970s was that quantum mechanics actually allows things to escape from the black hole. Okay, that maybe we'll discuss at a later point. But as far as typical classical theory, but usually that information that comes out is scrambled. Okay, so it's very unlike what went in. If your roommate went in, it's probably going to be destroyed into quantum particles and come out. Okay, and somehow those quantum particles, it's an open question how the distribution of quantum particles contains information about your roommate that went in, and maybe if you work hard enough, you can build them back together from those quantum particles. But basically, they're gone. Okay, and this is a very negligible effect. So the classical theory works really well, and anything that crosses the horizon of the black hole, no experiment outside the black hole can tell what happened to those objects. So it's really a region of space-time that is beyond your experimental reach. Okay. So now the question is, does such a region really exist? Well, as far as you're concerned, no. Okay. But in principle, if you want, you can dive in after them and see what happens. Right. It's just that as far as you're concerned, there's no experimental test that you can do which will tell you about it. Yeah. In fact, this is something that's rather strange about GR. Okay, it tells you that there are horizons, regions that you cannot cross. This is something that you also encounter in cosmology, that there are regions of space-time which we will never encounter. But mathematically, if you continue the geodesics, those regions exist. So the question is, do you want to attribute a reality to regions which you will never experimentally test? Okay, you could say that it's an uninteresting question because I'll never be able to test it. Okay, but from a mathematical self-consistency standpoint, these regions seem to exist. Okay, so this is something called the multiverse hypothesis also. Okay, and again, just like in, I mean, there have been cases where people have proposed tests of how you might see, let's say, a collision between our universe and these patches of the universe which are very far away from us. But again, in exceptionally rare circumstances, it's possible that you might see such a signature, but not guaranteed. Any other questions? Okay, thanks. I'll see you on Monday.